All right, guys. So let's start our 1.7 integration by parts. Now, integration by parts is something that you use when substitution method fails. Now, just to give you an idea of what that would look like, let me insert a page and just work a quick problem. So let's say we have 2x times sine of 3x minus 7 dx. Okay. Now, just like what we talked about with lesson 1.6d, which was substitution method using trig functions, if you have a single trig function, then you're going to get rid of the inside of the trig function. Take the derivative of that, and then that's going to give us 1/3 du dx. Okay? So if I plug everything back into my problem, this will give me the integral of 2x times sine of u times 1/3 du. I pull that out front, 2x over 3 times the integral of sine u du. Okay. Now right here out front is the problem, that 2x over 3. We talked about that when we were going over substitution method last week. If that fraction out front contains any x's or r's or any letters, then we've messed up. Well, we haven't messed up. It's just not going to work. And so that's a situation where we have to go to integration by parts. So that's what we're going to be talking about today. It's a little bit more involved than substitution method, and you only use it if substitution method has really fallen apart. Okay, now integration by parts can only be used when you have multiplication. So right here is the official definition, but let's kind of get to some examples so you can kind of see what all these letters actually mean. Okay, so right here, integration by parts only works when you have two things being multiplied together, A times B. That's the only time that it works. So if you have three things being multiplied together, it's not going to work. Okay. Now, if you have a fraction, there is a way to make a fraction work. So if you encounter that, just let me know. I'll kind of talk to you about how you can make that work. But there is a way to make a fraction work in some situations. But it only works for multiplication. Now, what you are going to do is you're going to take the derivative of one of these and you're going to take the integral of the other. And you have to decide which one. So what are the rules? So let me go back to this page back here and maybe write in another one. Rules for picking u. Okay. So rule number one, if you have an ln that is your u. So if your problem has an ln in it at all, that's your u automatically. No questions, no whatevers. That's your u. Okay. 2. If you have something to a numerical exponent, And by numerical, I should probably say integer or positive integer exponent. But no no ln, then that is your u. Okay. If you don't have either of those, then really it's probably not going to matter. I'm not saying it won't matter, but odds are you've got sine or cosine and e raised to a power, and then it's not going to matter which one you pick to be u. Okay, so that would be number 3. If you do not have ln or a positive integer exponent, then good luck. And it's your choice. What is u? Now, is that completely and totally accurate? No. You can come up, I'm sure there's a math person watching this going, oh my gosh, I can't believe that's what he said. One, yes, I know there are an infinite number of contrived examples that you could come up with where even if you do not have an ln or positive integer exponent, that it does matter what you pick. But let's be realistic here. Let's think about calculus 4 situations. Let's think about where this is going to be used in statics and in classical mechanics. You are not talking about contrived situations. You are talking about sine and cosine to a power, or you're talking about sine of something, you're talking about e to a power, or you're talking about x raised to a power. Those are the classical solutions to differential equations. You are not talking about some contrived situation that you could come up with to prove me wrong on these general guidelines. These are general guidelines. They are not set in stone. But after decades of experience taking derivatives and doing partial derivatives and integration, these are the 3 rules that I've learned about integration by parts. Okay, so take it with the intent. Okay, so right here, I do not have ln, but I do have a positive integer exponent with 2x to the first. Okay, so I'm going to let u equal 2x to the first. Then I'm going to take the derivative. So that's going to be a 2. Now, unlike substitution method, I am not trying to get dx alone. I'm trying to get du alone. So this is really du over dx is equal to 2. So the dx goes over, and I get du equals 2 dx. Now, once I write the formula down, you'll see why that is. Okay, but I'm not trying to get dx alone with integration by parts. Now for the integral, that's the letter v, and we are taking the integral of b. And so for us, that's going to be e to the 5x. And we do not need a plus c. Okay, so a couple things we need to write down. First thing, we want du by itself and not dx. This is different than substitution method. It's similar but different. And that step right there, that step alone causes more confusion over than what to let u be or what to let v be. Same thing down here. We do not need a plus c yet. So those are the two things to keep in mind. Now that we have this, let's look at what we're dealing with. So here is our original problem. We have the integral of 2x times e to the 5x dx. Okay. Now here's the integration by parts formula. U times v minus the integral of v du. Okay. So here's my pieces that I've got to plug in. I've got to plug in a u, two v's, and a du. So if I look at my stuff, u is equal to 2x, v is equal to 1/5 e to the 5x, v is equal to 1/5 e to the 5x, and then du is equal to a 2 dx. Okay, so I've got everything plugged in. The stuff out front is just going to be simplified. Nothing more, nothing less. So this is going to be 2x, well, 2/5 x e to the 5x. That stuff out front, that first chunk, that's just along for the ride. No big deal. Okay. Then right here, I'm going to pull out the 1/5 and the 2. So that's going to be 2/5 times the integral of e to the 5x dx. Okay. So I'm just going to take that integral a second time. And now I plug in my plus c. Now, I'm almost done. This is pretty much it. I am going to factor out some stuff here. So let's look at this. Each piece has a 2/5 and an e to the 5x in common. So I'm going to yank that out. And factor. So here's my final answer. Now, you might be asking yourself, does it really matter to pull out the 2/5 e to the 5x? In Calculus 2, no. In Calculus 4, yes, because I'm going to ask you to solve that, or I'm going to ask you to find the plus c, or I'm going to ask you to do something with that next. And when things are factored, they are easier to work with. That is fact, okay? There is very few contrived situations where factoring something makes it harder to work with. Usually it involves fractions. Factoring a fraction usually doesn't help, but even there, most of the time, you can still try to do something with that. So do keep that in mind. All right, so let's look at another example. Once again, we do not have an LN. LNs are rare. And when you get to calculus 4, you'll see why. LNs typically only occur when you're trying to take the integral of a fraction, and most of the time we are not trying to take the integral of a fraction. And once you start talking about second order differential equations, regardless of the form, the assumed general solution never includes an LN. The assumed general solution is going to be x to a power, e to a power, or sine or cosine. At no point do they ever assume a natural log as the solution, so they only really occur when you're doing stuff like Laplace multipliers, Laplace transformations, or something along those lines where you've got a fraction. Okay, so that first rule is one that rarely comes up, but I do have an example in here coming up, so don't worry, we will get to it. So this right here is going to be my u. That's just going to be rule number 2. So that's going to be u is equal to 5x. So u prime, the derivative, is equal to 5. And just like we did before, that's du over dx is equal to 5. I'm going to move that dx over, so du is equal to 5 dx. All right. So that gets me most of it. And v is going to be equal to the integral of sine of 3x. Okay. If we look at the integral table, that answer is going to be negative 1/3 cosine 3x. Okay. Now remember, we do not need our plus c right now. Right? So that gives us our u and our du and our v. Remember, we need 3 things with integration by parts. With substitution method, we only needed 2. So here's what we have. We have the integral of 5x times sine of 3x dx. All right, and that is going to be equal to u times v minus the integral of v du. Okay. So if I plug all that stuff in, that's going to be 5x times negative 1/3 cosine 3x minus the integral negative 1/3 cosine 3x times 1/5. No, I'm sorry, 5, just a regular 5 dx. All right, so let's zoom out just to make sure that I've got everything just right. Okay. All right, so let's simplify this stuff out. So that's going to be negative 5/3 x cosine 3x. Pull out the negative 1/3 and the 5, that'll turn that positive, so that's going to be positive 5/3 times the integral of cosine 3x dx. All right, so that's going to be negative 5/3 x cosine 3x times, not times, plus 5/3 times 1/3 sine 3x plus c. All right, so Now that I've gotten to here, each piece does have a 5/3 in common, right here and right here. But if all you're doing is pulling out just one number, factoring is typically not worth it. Now, there are times where it is, don't get me wrong. But for the most part, this is not going to help us. So I'm just going to leave it as one large piece instead of trying to break it apart. So that's going to be negative 5/3 x cosine 3x plus 5/9 sine 3x plus c. Factoring out a 5/3 is not really going to do much for this problem. All right. Any questions about that one? Any questions at all? All right. Now we finally come to an ln. All right. So if you have an ln, that is automatically going to be your u. Automatically. So that's going to be u is equal to ln 4x. We're going to take the derivative. So the derivative of u is 1 over what's inside times the derivative of what's inside. Okay, which will cause some cancelization. And so the derivative 1 over x. Okay. And so that's going to give me du over dx is equal to 1 over x. Move that over. So du is equal to 1 over x dx. Okay. Oh, my screen just changed. Why did my screen change? Okay. I'm still broadcasting. All right, good. All right. So that means my integral is going to be 6x. So that's going to be v is equal to the integral of 6x dx. So v is equal to 3x squared. All right, now that I have everything figured out, I can come back and work my problem. So my integral is 6x times ln of 4x dx. So that's going to be equal to u times v minus the integral of v du. Okay, so u is equal to ln of 4x. V is equal to 3x squared minus the integral of 3x squared times 1 over x dx. Okay. So this is going to give me 3x squared ln 4x minus, now that 1 over x will cancel out one of the x squared, so that's going to be 3 times the integral of x dx. So this gives me 3x squared ln 4x minus 3 times 1/2 x squared plus c. All right, give everyone a second here to get up to here. That step right before this one where that x squared times 1 over x became an x, that is what gave people a lot of trouble in the past. So take a moment, look it over, see if you have any questions about it. Okay. All right, now right here, let's look and see what we can pull out. Looks like we can pull out a 3 and an x squared out of both pieces. And so this will give us 3x squared times ln of 4x minus 1/2 plus c. All right, so we were able to factor some pieces out that made it worthwhile to actually do some factoring. All right, any questions about this one? Any questions at all? Yeah. All right, so let's do one real quick where we actually have a start and a stop. Now, I do want to remind people, if you have a start and a stop, you can use your calculator from the beginning, okay? But I do just want to remind people what it would look like if you had a start and a stop. So let's do our substitution. I think this is one we've actually already done. Let me go back and see. Did we already do this one? Nope, that was 2. All right, so close. I was getting ready to bypass a whole lot of work here, but no, we didn't. All right, so u is going to be 4x. So u prime is 4, and du is equal to 4 dx. And that is the shortcut. Whatever is the derivative, that just tack a dx on, and that is going to be your du. And then v is equal to the integral of e to the 2x dx. So v is equal to 1/2 e to the 2x. All right, so we've got the integral from 1 to 4 of 4x times e to the 2x dx is equal to u times v minus the integral of v du. And so that's going to be 4x times 1/2 e to the 2x minus the integral of 1/2 e to the 2x times 4 dx. So that'll be 2x e to the 2x minus 2 times the integral of e to the 2x dx. So this will be 2x e to the 2x minus 2 times 1/2 e to the 2x. Now I'm not including a plus c because we actually have a start and stop. So here in just a second, I am going to be able to plug in my start and stop. Okay, so here is the integral. So that's step 1. Step 2, I have to plug in my start and stop. So let's just copy this piece right here. So this is equal to 2x e to the 2x minus e to the 2x. And we are integrating that from x equals 1 to x equals 4. Okay, so the top goes in first. And then the bottom goes in. All right, so this is going to give me, let's just do 8 e to the 8 minus e to the 8. That's a 1 e to the 8. Distribute that. So that is minus 2 e to the 2 plus 1 e to the 2. Combine like terms, so that's going to be 7 e to the 8 minus 1 e to the 2. And if you have a calculator on you, you can type that in. And I do have a calculator. 7 e to the 8 minus 1 e to the 2 is a fairly large number, 20,859.317. All right. Any questions about this one? Any questions at all? And while you guys are getting caught up, I'll just type the original problem into my calculator and see if we get the same answer. We should. Or very close to it. 1 to 2. Come on, calculator. No, we did not. So I must have messed up somewhere along the way, because my calculator did not give me that answer. I might have messed up in some of this. No. Well, we'll see. Maybe calculator can't handle that. But I could have also messed up somewhere in this. U is 4x, then the 1/2 cuts that down. Oh well. Well, we'll worry about it a little bit later. I may have to add in a disclaimer if I see a mistake that I've made. Or I might have typed it into the calculator incorrectly to get that 20,000 mark. All right. So let's look at the next one. All right. So if your exponents are high enough, like right here, you may have to do integration by parts twice. So on this one right here, we'll go u equals x squared. So the derivative is 2x, and then that's just going to be du equals 2x dx. So there's the shortcut there. Then v is going to equal the integral of e to the 2x. Dx. All right. Oh, I know what I did on this one. I put a 4 right there instead of a 2. That should be a 2. I messed that up. I just noticed that should be a 2 right there. That makes all the difference in the world, and that 20,000 completely goes away. And that's 7 times e raised to the 4th minus 1 e to the 2nd And that's a lot better. I still don't know if that is the same answer I get. It's not. It's still not the same answer. Oh, I forgot the 4 right here. So that's not a 7. That's a 2, 4, 3. All right. Now it's going to work out. Lots of mistakes on this one. There we go. Now it matches. All it takes, guys, is just one small overlook, and you're out the door. And you're think about that. One small number was off, and my answer went from what it was supposed to be, 156, to 20,000. One number was off, and it went from 156 to 20,000. And let's completely fix that because it needs to be fixed up here as well. That is unbelievable. Look, I put that 4 in so many different places. Come on. There we go. Oh my gosh. That was such a big deal for one number. One number was off. And people are like, oh, it won't matter if your number's off a little bit. What's the big deal? That's a big deal. And I always tell people, it's like, if you don't think something's a big deal, imagine that's your paycheck. People really start to understand how important stuff is when you start talking about money. It's like, oh, well, I could pay you $156 for today's work, or I could pay you 20 grand for today's work. Oh, I'll take the 20 grand, please. Who's going to say no to that? So that right there is where things really start to get clear, is when you start relating things to money. All right. So that was x squared times e to the 2x dx. So this is going to be equal to u times v minus the integral of v du. So that is going to be x squared minus times 1/2 e to the 2x minus the integral of 1/2 e to the 2x times 2x dx. Okay, so let's simplify some things. So that's going to be 1/2 x squared e to the 2x minus the 2 and the 1/2 cancel each other out, x times e to the 2x dx. Okay, so let everyone get to here because now we're stuck. Now we are right back to an integration by parts problem. This right here, I'm sorry, still an integration by parts problem. So I'm going to have to go off and do that on its own. So let's go over to the next page. So I have the integral of x times e to the 2x dx. So I'm just going to take that smaller integral and come over here and do integration by parts again. U is going to be equal to x, so the derivative is 1, so du equals dx. Okay. V is still going to be equal to e to the 2x, and so V is equal to 1/2 e to the 2x. All right, so I am just doing integration by parts a second time. That's all I'm doing. Okay. So let everyone get to here. Now, I haven't taken care of factoring yet, and I have not added a plus C yet. Okay. So I'm getting ready to. I'm just going to wait until I put all the pieces together. Okay. So now we put both problems together. So let's go back to the previous situation, previous page here. So let's take all of this and copy it and paste it. Okay, let's delete some stuff here. Don't need that. Don't need that. Okay, so let's move this up a bit. All right. Okay. And so what's going to happen is this stuff right here, this right here, comes down to this. We have just found that part. So this is equal to 1/2 x squared e to the 2x minus 1/2 x e to the 2x minus 1/2 times 1/2 e to the 2x plus c. Okay, and so that's going to give me 1/2 x squared e to the 2x. Let's distribute that, minus 1/2 x e to the 2x plus 1/2 times 1/2 e to the 2x plus c. And so let's factor out my pieces here. I can factor out a 1/2. Holy crud, this is not going to give me a good platform to write on. Can I scoot any of this up a little bit? Just a touch. Nope. Okay. So I can pull out a 1/2 and an e to the 2x. All right. And so there's the final answer. Now, these take a while. And I've had them before where my original problem started as x to the third power, in which case you have to do it 3 times, or x to the fourth power, in which case you have to do it 4 times. And when you get those types of integration by parts problems, you really dislike integration by parts. It will work, but it takes forever to make that happen. All right, we've got one more example. And this one is a contrived situation. So this is very similar to a question we got last week in class, where someone asked if it was possible to ever have, after you get done doing substitution method, is it possible to have something left in the E other than just U or just whatever? And yes, it is. But it is a contrived situation. I am contriving this. This is not something you would see in real life, or I've never seen it. This is something I specifically made up to torment you and to prove a point. That's it. Okay. So this particular problem looks very, very complicated. But what I want to show you guys is how factoring can really help you out. So the first thing I'm going to do is I'm going to take my original problem, and looking up at the exponent, I'm going to factor out a 3. Now, I am now going to get rid of not the exponent itself, like we did with substitution method. I am just going to get rid of the inside of the parenthesis, and that's it. So I'm going to choose a new letter to get rid of. R equals 2x minus 7. So R prime is equal to 2. So 1/2 dr is equal to dx. I'm using the letter R instead of the letter U because U is in my integration by parts letter. So I'm just trying to do that. So this is going to give me the integral of R times e to the 3r dr. This is now an integration by parts problem. Okay, so I'm just going to take it and go to the next page. Hit the wrong button. There we go. All right. So imagine R was X. I'm just going to let the letter U equal R. So U prime equals 1 and du is equal to dr. And then V is equal to the integral of e to the 3r dr. Now, if you're struggling with this, ask yourself this question. Are you struggling with this because this is so difficult? If you are, then let's be honest, this is just the first problem. This is just the first problem all over again. That's all it is. Instead of the letter X, I have the letter R. So Ask yourself, are you struggling with this because it's such a difficult problem? Or are you struggling with this particular page right here simply because it's the letter R? And no judgments. I just want you to be honest with yourself. If it's because it's the letter R, then this is one of the reasons why I'm working this problem. Because I've had no telling how many science teachers come to me and tell me, my students don't know the math. And then I'll suggest to them, I'll ask them, well, what letter are you using in your problem? And they'll say, well, I'm using T, or I'm using L, or I'm using omega. And I'll be like, just let's do an experiment. Next time you have class, just use the letter X and see how many people feel better about the math. And they'll go and they'll use the letter X or the letter Y, and they'll be like, now they can work the problems. I was like, okay, so the issue is not that they cannot do the math. The issue is that they're not used to the letter other than X and Y. And so that's part of what I'm doing. I'm trying to get you guys used to other letters, because science, the math is what you're doing. You can do the math. It's getting you used to these other letters that in science they are going to use. All right, so let's get back to this one. So this is going to be u times v minus the integral of v du. So let's plug that stuff in. That's going to be r times 1/3 e to the 3r minus the integral of 1/3 e to the 3r dr. So this is going to give me 1/3 r e to the 3r minus 1/3 times the integral e to the 3r dr. Almost done. All right. Now, normally we would be done here, but I do just want to remind you guys that r is equal to 2x minus 7. So let's do a recall that r equals 2x minus 7. So this is equal to 1/3 e to the 3 times 2x minus 7 times 2x minus 7 minus 1/3 plus c. So that is going to give me 1/3 e to the 6x minus 21 times 2x, and then a take away 7 and a take away 1/3. Is take away 22/3. There we go. There's the final answer. So you will not see one like this on your homework. I wanted to work this one mainly just to expand your horizons. This one is a completely made up problem, I do not ever expect you to encounter something like this in real life. Doesn't mean you won't. Doesn't mean you won't. But I do want to kind of introduce you to how some of the advanced substitution works, how you can have both substitution and integration by parts. Because when we get to some of the trig stuff, we will have both substitution and trig rules. So you're going to be combining things together to get a overall general solution. So I want to get you used to not thinking about there being one right answer or one path to a right answer, but how you may have to combine multiple paths to get to your correct answer. All right, so we're going to stop there, and you guys can start looking at the homework, and I will make some more videos. Have a good day.